Up to this point, we've only talked about atoms as being neutral, as having the same number of electrons as protons. However, in many cases in compounds, this may not be true. Atoms can gain or lose electrons. Now, they cannot gain or lose protons because that would fundamentally change the identity of the atom, and it would become a different element, which would violate one of Dalton's postulates. But they can gain or lose electrons. And when this happens, when atoms gain or lose electrons, the result is the formation of an ion. Two examples are shown here. We can start with a sodium atom that has 11 protons and 11 electrons, so it's neutral. If it loses an electron, we will form a positively charged sodium ion. Alternatively, if we have chlorine atom, this has 17 protons and 17 electrons. If we gain an electron, we can now form a negatively charged chlorine ion. Now, positively charged ions are referred to as cations. Negatively charged ions are referred to as anions. And we can help ourselves keep track of this nomenclature simply by these kind of memory devices here. Cats are good or positive, and thus we have cations are positive. Onions are bad or negative, and so anions are negative. Now, when we talk about atoms gaining electrons or losing electrons, certain atoms fall into two categories about whether they will gain or lose an electron. And metals lose electrons to form cations. Nonmetals gain electrons to form anions, and those are generally the separations. And then we can take those positively charged cations and negatively charged anions, and if we bring them together, we can form what's known as an ionic compound. And that is a compound that is composed of a cation and an anion. It has to be neutral, so the charges have to balance each other out. And an example here is something like table salt, sodium chloride. You have a sodium, a positively charged cation, and a negatively charged anion that come together to form an ionic compound. Now, how exactly does this process work? Well, we can look at the periodic table itself and be able to predict the magnitude of the ionic charge that any individual atom will form. Group 8 noble gas elements are generally non-reactive, so they do not participate in this gaining or losing electrons. And because they are so stable, most other elements would like to have the same number of electrons as the noble gas elements. So when we look at the periodic table, we'll see that atoms gain or lose electrons in order to reach a number that's equal to the group 8A, or remember, this is also group 18 element. So here's just a quick summary. What we'll see is on the left, the lithium, sodium, the alkali metals, they only have one more electron than the noble gases. So the noble gases are over on this side. Remember, the periodic table is arranged in order, left to right, increasing atomic number, which means also increasing number of electrons. And so the alkali metals have one more electron than the previous row's noble gas. So if those elements will simply lose one electron, they will now have the same number of electrons as a noble gas. And then, so these elements, the alkali metal elements, only form +1 charges. The alkaline earth metal elements, on the other hand, they need to lose 2 electrons in order to get back to have the same number of electrons as the noble gases. And so it's the charge that alkaline earth metals will form is a +2 charge. Again, these are metals, so they lose electrons. If we wanted these to gain electrons, they would have to gain 7 electrons for lithium to have the same number of electrons as a noble gas. It's much easier to lose 1 electron than it is to gain 7. Over here on this side, remember that aluminum is on the left side of that dividing line. And so it's a metal. Metals lose electrons, and so aluminum will lose 3 electrons to get back to the same number of electrons as a noble gas, rather than gaining 5. On the right-hand side, the nonmetals gain electrons, remember, and so the halogens, fluorine, it's only 1 electron shy of having the same number of electrons as a noble gas, so it will gain 1 electron and form a -1 charge. Oxygen, however, has to gain 2, and we can sulfur has to gain 2, nitrogen has to gain 3 in order to have the same number. And so based off this, we can just look at the periodic table and determine the charge for many of the metals and nonmetals. Now you will notice we leave out the transition metals, which are these middle block here. Those are much more difficult to predict. We can't just look at the periodic table and count a certain number of electrons from there. And so we don't include them in this way. But there's one other element to highlight that behaves a little uniquely, and that's hydrogen. Hydrogen can both lose an electron or gain an electron. It's really unique in this fashion. It is a nonmetal, so we might think of it as gaining an electron to form H minus, a -1 charge. But because it only has 1 electron, period, it's also fairly easy for it to just lose that electron and just be left with normal hydrogen just has a single proton in its nucleus. And so hydrogen is unique in that way. But this allows us to predict, simply by looking at the periodic table, the charge that any element would form in an ionic compound. So then let's put this together. How are ionic compounds actually formed? Well, ionic compounds are composed, generally speaking, of metal cations with nonmetal anions. There are a few cases of nonmetal cations. We'll talk about that later. But the vast majority of cations, the positive charge, are metals, and anions are nonmetals. So an ionic compound is formed by bringing those two together. We form ionic compounds by doing an electron transfer from the neutral atom. So if I start out with a neutral sodium atom and a neutral chlorine atom, I will give up the electron from sodium and give it to the chlorine to form the cation for sodium and the anion for chlorine. And that is where I get my two ions, the cation and the anion. And again, my metal, the sodium, is what forms the cation. My nonmetal, the chlorine, is what forms the anion. Now, when these two ions come together, and this is true for all ionic compounds, we form this 3-dimensional lattice of anion, cation, anion, cation, anion, cation in both the horizontal direction and the vertical direction. And as a result, there is no discrete molecular formula for this compound. All we can give instead is an empirical formula for this. We can say that the smallest whole number ratio of these is 1 sodium and 1 chlorine, but we can't say that there's any discrete molecular formula for this compound, and that is true for all ionic compounds. Now, how does this work in terms of predicting? If I said, oh, we'll make an ionic compound between here this random metal and this random nonmetal, how would I know exactly how to combine them? Sodium and chlorine seem somewhat straightforward. You simply you make sodium the cation and chlorine the anion and then just bring them together, but it's simply a 1-to-1 ratio, so that's fairly easy. But how do we do this for other systems? Well, we can predict the ratio of the different anions by looking at the charges. Remember that the final ionic compound has to be neutral. We have to have charge balance. And so we can do this by looking at the charges that we're given. So if we take the charge of the cation and look at its magnitude and make that magnitude be the subscript of the anion, be the number of atoms of that element. I do the same thing with the charge of the anion and bring it over to make it the subscript, the number of atoms of the cation. we can then form a charge-balanced compound, because if I have 3 magnesiums, each magnesium has a +2 charge, so that gives me a total of +6 charge. And I have 2 nitrogens. Each nitrogen has a -3 charge, that gives me a total of a -6 charge. And so if I combine the compound in this way, magnesium, 3 magnesiums, 2 nitrogens combined together, that will form a charge-balanced discrete ionic compound. A couple other examples here. Calcium is an alkaline earth metal, so it has a +2 charge just by looking at the periodic table. Fluorine is a halogen, it has a -1 charge. So the 1 comes down to be the subscript for calcium, the 2 comes down to be the subscript for fluorine, and I end up with calcium with 2 fluorines to form the charge balanced ionic compound. Lithium and oxygen can behave the same way. +1 charge becomes 1 oxygen, -2 charge becomes 2 lithiums, and so we end up with lithium 2O, 2 lithiums, 1 oxygen. There is one caveat with this that we must pay attention to, and that is that the reported formula must be the empirical formula. Because ionic compounds don't exist as molecular formulas, they exist only with empirical formulas. We have to make sure that when we do this, when we take the magnitude of the charge and bring it down as a subscript, we have to make sure that the final result is the empirical formula. An example here would be something like titanium 4+ with oxygen 2-. If you do this initially, you come out with Ti2O4, but that is not the smallest whole number ratio. So you would divide this by 2 to get TiO2 as the empirical formula for the compound. Let's do a couple more examples. So we've got 2 here. Predict the charge expected for the most stable ion of phosphorus. Well, you can pause now and pull out your periodic table and look for phosphorus and see that phosphorus is in the same column as nitrogen. It's a non-metal, so it's going to gain an electron. It's going to gain electrons. It's going to become the negatively charged anion. And how many electrons is it going to gain? Well, it's going to gain the number of electrons that will give it the same number of electrons as a noble gas. If you look at where phosphorus is, it needs to gain 1, 2, 3 electrons to have the same number of electrons as a noble gas. And so here we would form phosphorus 3-. Second question is predict the empirical formula for an ionic compound involving combination of calcium and phosphorus. Well, the first thing we need to do is figure out what's the charge for calcium, what's the charge for phosphorus. Well, we just figured out the charge for phosphorus. It would form a 3- charge. Calcium, we did that on the previous page, that had a +2 charge. And so if I have a calcium 2+, phosphorus 3-, I bring those superscripts down to become the subscripts of the other atom, and I would come out with a calcium 3, phosphorus 2 ionic compound that would be charge balanced, and this is the empirical formula for this compound.